The first order rate constant for the decomposition of dinitrogen pentaoxide at 70 degrees Celsius is 6.82 times 10 to the minus 3 per seconds. Suppose we start with 0.025 moles of N2O5 in a volume of 2 liters. A, how many moles of N2O5 will remain after 5 minutes? All right, so when we bring a time component into this situation, we're using the integrated rate law. So they told me it was a first order relationship. They told me what the rate constant was. They told me moles. They told me volume, so I can get the concentration. So this is my initial concentration. I know what the rate constant is. What I can do with this is plug into the integrated rate law for a first order reaction and solve for what the concentration is going to be at time t. So I know how much time went by, and I know what the rate constant is, and I know what my initial concentration is. So I can plug into this and solve for what the concentration is going to be at time t. And that's the power of the integrated rate law. They didn't want the concentration, they wanted moles. So use liters to convert from moles per liter to moles. So that's how many moles you're going to have after 5 minutes. B, how many minutes will it take for the quantity of dinitrogen pentaoxide to drop to 0.01 mole? All right, so I know what I want to get to and I know where I'm starting from. So divide by 2 liters and I can get what the concentration is at time t. I know what my initial concentration is. What I want to find is how much time went by, right? So this is really, really cool. I mean, the power of this is if I know what concentration I'm starting with, what concentration I want to get to, and I know what the rate constant is, I can plug into this and solve for how much time has to go by in order to get that concentration. So when I solve for t, it's in seconds. They wanted it in minutes, so I can solve for how many minutes went by. All right, C, what is the half-life of N2O5 at 70 degrees Celsius? All right, the beauty of a first-order rate law or first-order rate relationship is that the half-life is independent of the initial concentration. So it doesn't matter what concentration I have. The half-life is always going to be the same. And it's related to the rate constant. So T1/2 is equal to the natural log of 2 divided by K. So if I know what the rate constant is, I can plug into this and solve what the half-life is. So if I want to have my concentration, I'd have to let 101.6 seconds go by. Or 1.69 minutes. All right, the reaction of SO2, Cl2 forming sulfur dioxide and chlorine is first order with respect to the reactant. Using the following kinetic data, determine the magnitude and units of the first order rate constant. All right, so we're plotting pressure versus time. So if they tell me it's a first order relationship, if I take the natural log of those pressures and plot them versus the times that they were taken, I get a straight line with a negative slope. The slope of that line is equal to the rate constant, right, according to the integrated rate law. So take the first point, take the difference between the natural log of the initial pressure and the final pressure, divide it by the change in time, and I get the magnitude of the rate constant. Consider the data presented in exercise 19. By using appropriate graphs, determine whether the reaction is first order or second order. All right, so number 19, right, A turning into B, they gave us moles and we had the volume, so we get concentration. We have different concentrations at different times. So if I plot the inverse of the concentrations versus time, I'll get a positive slope, and this will tell me it's a second order relationship. If I plot the natural log of the concentrations versus time, I'll get a straight line with a negative slope, and this will tell me it's a first order relationship. So this is how we can determine whether we're dealing with a first order or second order relationship based on concentrations that aren't being doubled, right, or tripled, and seeing how it affects the rate. So that's not always possible, right, with a particular reaction. So you'd have to plot them. Take the inverse. We'll first get the concentration, plot the natural log of the concentration, take the inverse of the concentration. If I plot the natural log of the concentration versus time, I don't get a straight line with a negative slope. So this tells me it's not a first order relationship. If I plot the inverse of the concentration versus time, I get a straight line with a positive slope. So this tells me it's a second order relationship. B, what is the rate constant for this reaction? All right, rate constant is going to be equal to the slope of the line. So it's a second order relationship. So take the inverse of the concentrations. Get the difference between the inverse of the first concentration, inverse of the last concentration, and divide by 40 seconds, the change in time, and get the rate constant. C was the half-life for this reaction. All right, half-life for second-order reactions is not concentration independent, right? It depends what the concentration is. So if I take the initial concentration and plug it into the relationship between K and half-life for a second-order relationship, I can get the half-life with this starting concentration. So first-order half-life is more useful. It's concentration independent. So if I know the rate constant, I know the half-life. All right, so I have reactants forming products measured over several temperatures, and the following data was collected. All right, so increase the temperature, increase the rate constant. That's true for any reaction. All right, all reactions go faster if you increase the temperature. So you're not changing the concentration, right? That's not what's affecting the rate here. It's the rate constant. So increase the write that down. Increase the temperature, increase the magnitude of the rate constant. So this is the Arrhenius equation. If I plug into the Arrhenius equation and I know what the rate constants are at the various temperatures they were taken, I can find the activation energy, right? How much energy I have to get past in order for the reaction to occur. So slope of the line is equal to negative activation energy over the gas constant. So if I plot the inverse of the temperatures that they were taken in Kelvin versus the natural log of the rate constants, I get a graph with a straight line. All right, and the magnitude of that straight line, or the slope of that straight line, is equal to the negative activation energy over R. So if I get the change in the natural log of the K values over the change in the inverse in temperature, and I get the slope, I can divide that, I can multiply that by R and get the activation energy. So this is the power of the Arrhenius equation. If I know what the rate constants are at the various temperatures they're taken, I can find out what the activation energy for the reaction is. What is the molecularity of each of the elementary reactions? Write the rate law for each. Okay. When I look at a balanced chemical reaction, I have no clue what the mechanism is for the reaction. I have to do experiments to figure out what the elementary steps are. That's not true for an elementary step, all right? So they're telling you elementary reactions here. These are elementary steps, one-step process. So it's the collision theory, right? Things colliding to form new things. So all I have to do with A is look at the fact that I have chlorine falling apart to form two chloride ions and recognize that this is first order with respect to chlorine. Doubling the concentration of that reactant will double the rate at which it's decomposing. B, I have two things slamming into each other, right? I have OCl- slamming into water to form, what is that, hypochlorite. Hypochlorite slamming into water to form hypochlorous acid and hydroxide. All right, so first order with respect to hypochlorite, first order with respect to water. If I double the concentration of these, I quadruple the opportunity for collisions. So it's a second order rate law by just looking at what the equation is for the elementary step. Same with C. Second order rate law, right? Double the concentration of chlorine, double the collisions, double the concentration of nitrogen monoxide, double the collisions. So this is how we deduce mechanism based on what the elementary steps are. There's rules about the mechanism, right? The sum of the elementary steps has to add up to the overall equation, and the slow step in the mechanism has to represent, or I should say, the rate law for the elementary step and the slow step in the mechanism has to match the overall experimentally determined rate law for the reaction. I hope that's clear. It'll be clear maybe in the next few problems.